Okay, so good evening and welcome to the 11th live session for Applied Linear Algebra. And so we'll continue our usual weekly sessions. This time we'll be focusing on the contents from week 11 and week 11 mostly circulated around the notion of stochastic processes, particularly Markov chains, as you have seen. And we have seen the discrete time case, not the continuous time version, but discrete time Markov chains, or DTMC for short. And in general, like stochastic process is nothing but a probabilistic model of characterizing a system in time. I mean, characterizing the evolution of that system in time, how it evolves with time. Any event or process that is random in nature, for example, you measure the temperature of some room, you check the status of a machine in an industry. We have looked at the explicit example of a industrial reliability problem. Remember, if you want to monitor the status of a machine, whether it's in operational state or in the faulty state, how it evolves over time. And similarly, we have seen other examples like the uh, stock market price. So how it changes with time. So anything that evolves with time can be modeled using this probabilistic model, and one such application is one such example is the one way to characterize or model them is using the Markov chains. So there can be discrete number of finite number of states, okay, and you can characterize them using something called the transition matrix, right? Transition probability matrix. It could be one step transition probability matrix or multi steps, some m step uh, transition probability matrix, or you can view it as some transition diagram, state transition diagram. Okay, so and we have looked at the Markov properties. What are the different properties? What is the Markov property, and then what is the time homogeneity property, and so on. Then we moved on to, the special case of limiting behavior of, Markov chain. And how can you comment about, the probability of a state being equal to some state Si as n tends to infinity, probability of xn equals to Si limit n tends to infinity. So, and we also looked at what a stationary distribution is, right? And then we also revisited the least norms method. Okay, so some simple proofs of, how YA needs to be full column rank and so on. And then I think we yeah, I think that's pretty much all that we have looked at. um, yeah, so yeah, let's get started with today's session. But I wanted to just clarify one of the doubts that we faced in our last session with respect to that calculation of a distance. So applied linear algebra. Okay, so yeah, first thing maybe like clarification of doubt from last session. So basically, that problem was, as I was like suspecting, we are making some error, some silly mistake. So the problem was that we essentially wanted to find the distance between two hyperplanes, and in our case those hyperplanes, I mean it was a special case of n equals to 2, which meant like there are two parallel straight lines in the two dimension, and you need to find the distance between them. And we have already studied in our like high school geometry that how to find compute distance between two parallel lines. So the problem was kind of like this. So we had extend it further. So let me call this y-axis and x-axis. Okay, the usual uh, axis. I mean, in our case, it was in the problem, I think x1, x2. So, but anyways, so in general, what is the distance between two parallel lines? You, let's say you have line 1 as ax1 plus bx2 plus c1. Sorry, here I am using x and y, our usual axis notation. So let's say a1x plus b1y plus c1 equals to 0. Let's say this is the equation of first line. Then you have a2x plus b2y plus c2 equals to 0. These are two straight lines in 2D. So now if I ask you what is the distance between these two parallel lines, and for parallel lines you also need one more thing, that these AIs and BIs should be equal, but C1 and C2 can be different. I mean, if they are same, then they are exactly the same lines.
Yes.
So if for parallel lines, okay, I'll maybe mention for parallel lines, A1 equals to A2, B1 equals to A2. I mean, it's not that thing, but I should not say they're equal, but their ratio A1 by A2 should be equal to B1 by B2, but that should not be equal to C1 by C2. I mean, it can be C1 by C2, but in that case, it's essentially, I mean, two same lines only. But yeah,
Means the slope is same, but intercept is not same.
exactly,
Yes.
exactly.
Yes.
Right? So you can rearrange it in terms of slope intercept form also, y equals to mx plus c, but the slopes will be the same, but I mean that is the slope is governed by the ratio of b and a, right? b1 by a1. So but the intercepts are different. That's why they are like two distinguishable lines which are not meeting, never meeting. So
Yes.
it could be multiple cases. Now let's say if I ask you to like um, and also like the distance of this first line, let's say this is L1, this is L2. The distance of the first line from the origin, if this is the 0 comma 0 point, let me denote it by d1, that is given by mod of c1 divided by square root of a1 square plus b1 square. Okay, this is like, and this is exactly the formula that we also used in our hyperplane scenario as well for the case of n equals to 2. And similarly d2 is equal to mod of c2, and whichever is that constant term, divided by a2 square plus b2 square. Okay, in our case a1, I mean these ratios are the same. So these are the two distances. Now since these ratios are actually equal, a1 a2 b1 b2, you can actually, make two lines exactly the same with respect to the coefficient of x and y, but only the intercepts as different. So you can ultimately treat them as ax plus by plus some k1 equals to 0, and then ax plus by plus some k2 equals to 0. Okay, these are two parallel lines in 2D. So it's a special case of hyperplanes. So now different cases may arise. If let's say one line is like this, the other is parallel to it but lying on the opposite side of the origin. In that case, you have to measure the perpendicular distance from the origin for both of them, and they will get added together because they are lying on opposite sides of the origin, right?
Yes. Yes, sir.
Yeah, whereas in our case it was like they are lying on the same side. I mean, it depends on the equations of the lines,
Hmm.
which you can simply just draw it. It's always a good practice to draw and plot them so that you get the y intercepts and the x intercepts. That way you can easily visualize how it looks like. So in our case it was like this. So what you have to do is you have to find the distance of the bigger distance, uh, the distance of the line that is farther away from the origin, and then you
Hmm.
find the distance of the line that is closer to the origin and subtract the
Hmm.
smaller distance from the larger distance. So that will give you the distance. So
Yes.
it depends actually. I mean, the overall distance between two lines, between two parallel lines, can be given by d. I can think of it as like k1 plus minus k2 divided by like this. So it might get added, it might get subtracted depending on their orientation. In our case, they were in the same side, so you can subtract the smaller distance from the larger distance. That's fine. But the problem which we were encountering is that, like, what I was doing is, I mean, I realized it, but I didn't mention it during that time. So we were finding these intercepts, okay, this point, say x1 y1 x2 y2, and similarly for the second line we were finding the intercepts x3 y3 and x4 y4.
Hmm.
Then what I was doing is I was drawing this perpendicular. That's fine, that's the common perpendicular to both of these lines because they are parallel. So if this is 90-degree, this is also 90-degree. Then I was finding this coordinate.
Hmm.
So what I was doing is I was labeling this coordinate as the midpoint of these two. So what I was doing is I was making this as equal to
Hmm.
this. But that's not true. That's not necessarily true
Hmm. Yeah.
because it is not necessarily the midpoint. It can cross this line at any arbitrary point that we have to figure out. I mean,
Hmm.
the slopes of two perpendicular lines is the product of their slopes is equals to -1. So using these two coordinates x1 y1 x2 y2, you can find the equation of this line, and this is one line. The perpendicular that you are drawing is a line through the origin, so it is something of the form y equals to mx. So
Hmm.
this m times the slope of this line. The slope of that line is y2 minus y1 divided by x2 minus x1. That should be -1. So that tells you what is the m, and you can find out what is y equals to mx, that equation of
Hmm.
the perpendicular, and then you can solve for them where they intersect, and then you can find this point of intersection. I mean,
Hmm.
you have, if you have to go all the way like geometrically calculate algebraically and so on.
Yes. Yes. Yes.
So this, the problem was lying in this calculation of this coordinate. And similarly, the error which we made here, I was treating this as x3 plus x4 by 2, comma
Mhm.
y3 plus y4 by 2, which is again the problem. So of
Okay.
course we are arriving at a wrong answer.
Mhm.
So but anyways, I mean, uh, the main point is that okay, you know the formula of the distance, and this is how it's given by like two parallel lines this case. And it's always better to, I mean, check whether they are lying on the same side of origin or not, and accordingly you decide this sign in the distance, whether they get added up or subtracted.
Yes.
So okay, I mean, this is the small, thing. And now, coming to today's session. So today's session, okay. So mostly it will be like based on Markov chains and all. So, and particularly we are looking at discrete time Markov chain, okay, and DTMC for sure. So you have some discrete number of states, some finite number of discrete states. Let's say some capital N number of states. So let's say S1, S2, all the way till Sn. Okay. So it's not continuous, it's discretized. Okay, that's why the name. And this is the collection of all the states, which is denoted by capital S, and it's called the state space. Okay, and there are n states. Okay, and whenever there are n number of states in a DTMC, this DTMC can be characterized using a n cross n square transition probability matrix. So if there are n states, there we have a n by n one step transition probability matrix denoted by capital P. Okay, and I mean, transition means like one state is changing from a state is changing from one to other. So let's say it's from S1 to S2. So that's why I use the word evolution. Okay, from S1 to S3 or Sn to S2, whatever. So the notation that we follow, and that is associated with the probability. That's why a probabilistic model to study these evolution. So we use the notation p suffix ij. So what is pij? So it means the probability that the state evolves from si to sj. Okay, the first index corresponds to the initial point, and the second index corresponds to the uh, state that it evolves to. Okay, so this is nothing but the probability that I started, let's say at time instant n. Okay, this suffix n, this n is the time instant. So let's say it means it evolves from si to sj. So I started from si. Given that I started at si, my next state, which is at the next time instant, which is n plus 1, it goes to sg. Okay, this conditional probability is basically this transition probability. Okay, pij, and this will be the I comma jth entry of this one step transition probability matrix. Okay, this is the same as, I mean, the I comma jth element of the one step transition probability matrix. So this is representing basically the probability of evolution from Si to Sj. Okay, and one more property that we have seen is the Markov property. What does the Markov property say? The probability that your next state, which is n plus 1 at time instant n plus 1, the state goes to Sj, given, your past states, which is like xn comma xn minus 1 all the way till, let's say I'm starting from index 0 or time instant 0 all the way till x naught. This is equal to the same as, you can actually discard all the
Previous ones.
previous ones. You consider only the most latest xn,
The last.
that is the most relevant state. Okay, you can
Yes.
ignore all this. These are not relevant. So this is nothing but probability of xn plus 1 equals to Sj given xn. This is the Markov property. And also there was like the time homogeneity property, which tells you that, I can put it in like a simple example, like probability of, let's say you are going from uh, n equals to 0 to n equals to 1, let's say. So this is one step transition from Si to Sj. This is also the same as from, it's independent of this n, this subscript. Okay, doesn't matter, like it's all the way equal to, where should I, this transition is independent of n, and it is actually equal to probability of xn plus 1 equals to Sj given xn equals to Si. Okay, so this is the time homogeneity property. Alright, so this was a quick summary of the discrete time Markov chain. Any doubts?
No, sir.
Okay, so then we shall begin with today's questions. So these are all very easy, simple questions. Okay, so let's start with the first one. So consider this one-step transition probability matrix, capital P, for a discrete time Markov chain, DTMC, given as this. Then we are asked to find what is the two-step transition probability for starting from state 2 and ending in state 1. Okay? Okay, just a second. And also, as we will see later, this matrix P, this transition probability matrix P, the entries of this matrix are essentially all probabilities, right? Because they tell you the transition probability. So they are non-negative, they are lying between 0 and 1. And also another property is that the sum of entries of every row is equal to 1.
Sum of?
Sum of every row of P is equal to 1. So I'll mention
Okay.
sum of entries of every row of P, this matrix P, is equal to 1. Okay, this is a property. You see, let's say P11 means, let's say there are two states, S1, S2. So P11 means from state 1 it goes to state 1. Let's say that happens with some probability small p. And there is only another one more state, S2. So what is the probability that S1 goes to S2? Is just 1 minus p, right? I mean, there are
Yes.
only two options for it to evolve. Either it stays at S1 or it goes to S2, because there are only two states. So
Hmm.
P11, if it is P, then P12 will be 1 minus P. So you can see the sum of these two probabilities is equal to 1. So it ensures for every such, rows of this transition matrix, the sum of the entries of the row should be equal to 1.
Okay.
Okay, so I mean, these things have been discussed in the lectures also. So the first one, okay, in the first question, you look at this matrix. This is a 2 cross 2 matrix. So that automatically tells you that there will be two states, because I wrote it here that if there are n states, then that probability transition matrix will be an n cross n square matrix. Here you have a 2 cross 2 matrix, so which means there are two states in your Markov chain.
Okay. There
If
is
it's n by
three.
n, there will be n states. If it's 3 by 3, there will be 3 states. Okay?
Okay. Yes.
Okay, I'll explain now. Okay.
Tell.
Now, one step. Why one step? Because it's just, I mean, at one step it is happening, like from S1 to S2. Okay, so one step transition probability matrix for DTMC. DTMC is discrete time Markov chain. This is given as, and feel free to interrupt me if at any point anything is not clear.
Yes.
This is the transition probability matrix. Okay, what does this mean? So this is 2 by 2. So my state space would be, basically you can think of it as, okay, just a second. Just a second. Okay. So yeah, let's, yeah, so as I was saying, so there will be two states here because it's 2 cross 2. Let me call them some S1, S2. This is my state space. Two states in DTMC. So what this entry, the first 1 comma 1 entry, what is this telling you? So P11 is 2/3, P12 is 1/3, P21 is 4 by 5, P22 is 1 by 5. Okay, so what is P11? What does that tell you? It's like S1 going to S1. I mean, it's S1 stays at S1 after one step with probability 2/3. State 1 stays at state 1. And what is P12? S1 going to S2. Okay, first index is the starting point, second index is the ending point. P21 means S2 going to S1 with probability 4 by 5. P22 means S2 staying at S2. Okay.
Yes. Yes. Yes, sir.
Okay. And you see here, for this matrix, you check the sum of every row. There are two rows. Sum of both rows is equal to 1. You consider the first row 2/3 plus 1/3, 1. Second row 4 by 5 plus 1 by 5 is equal to 1.
Yes.
And also all entries are just probabilities because they are transition probabilities. probability of one state going to another state, and they are all these Pij's are lying between 0 and 1. So okay, okay. And as I said, it makes sense because some of the rows should be 1, because P11 plus P12 must add up to 1, because S1, I mean, it has only two possibilities. Either S1 can stay at S1 or it can go to S2. There are only two states. Okay, so therefore there, I mean, the probabilities must add to this. These are the two only probabilities, these are the two only possibilities of events that can occur, so they must, their probabilities must add up to 1. Similarly for state 2, if you are starting with state 2, consider this second row. If you are starting with state 2, you can either stay at state 2 with probability 1 by 5, or you can go to state 1 with probability 4 by 5, and the sum of them is equal to 1. Now you are asked about this thing, two step. So this matrix is the one step transition probability matrix. Okay, the two step means, let's say, from S1 to S2 to S2 again, or S1 to S2 to S1. It's like that in two steps. So the two step transition probability for starting, so starting, okay, we rewrite starting. What is the two step transition probability if you start from state 2 and end at, or end in, state 1? Okay, so this can happen in two ways. You start in state 2 and end in state 1, and you reach state 1 in two steps. So what are the two possibilities?
So initially we are assuming that it is in state 2 and it is coming to state 1, but if it is in state 1 then it will remain in state 1. That is also
Yeah,
possible.
that's fine, that's fine,
Uh,
but in the question you are asked, like, if this is the case, what is the step transition, two step transition probability if you start from state 2 and end in state 1? Okay, this, let's say this is an event happening, what is the corresponding two step transition probability? Okay, so that is the question.
okay,
Here
but
you're starting in state 2 and ending in state 1 in two steps. So there are two possible sequences for this, right? I mean, you start,
I'm not getting how you can have two transitions, because for P21 we are saying it is going from S2 to S1.
yeah, yes. Now, what is your doubt?
Two-step transition. So it is not like S3 to S2 and S2 to S1. It is not like that.
No, no, no. There is no S3 in the picture. There are only two states. Okay, S1, S2. These are two states. And steps means
Okay.
like the
Okay.
number of
S1 and S.
transitions. Okay, number of transitions that is happening. Okay,
Hmm.
so you are, let's say this is your starting point is S2, which is given, or this is an event which is given to you. Just think of it as a probability problem. What is the probability of getting a heads in a coin toss? So the event is getting a head in coin toss. What is the associated probability? The question is also the same thing here. You are given, like, you are starting from S2, state 2,
Hmm.
and then in two steps, in two steps you are going to final state is state 1, ending in state 1. Okay, so as you're seeing, like there are two arrows,
Mm-hmm.
and which means two number of transitions happening, so two steps. Okay, so what is the probability of this event? So let's say this is the event which has happened, so this is the probability. What is the probability of this event? Okay, so now what can be the possible paths, like S2 to S2 to S1? Okay, so let's say after the end of one step it stays at S2, but on the next step it makes a transition to S1, or it can happen at the end of first transition or first step it goes to S1, and then it at the next
Mm.
transition it stays at S1. So these are
Yes.
the two possible paths,
Yes.
correct?
Yes. Understood.
Right, so these are the two possible like events and which can happen. So you have to find the corresponding probability, and I mean there are two possibilities, which means I mean you have to add them up, right? So
Yes.
let's say you um, um,
Plus two.
okay, so these are the two cases.
Okay.
That's what you do, right? I mean you add these probabilities, right? Let's say you uh, throw a dice two times, and then let's say you want to check that the sum of the two digits appearing should be even. Then you look for all those cases, no, like 1 comma 1, 2
Huh.
comma 2, 1 comma 3, so on all the way. So you add them up, add these individual probabilities. So the probability of getting 1 comma 1 is how much? 1 by 36, right? This is one event. Probability of this event to occur is 1 by 36, because like
Hmm.
tossing, like throwing a dice two
Hmm.
times, it's like total number of outcomes could be 36, right?
Hmm.
There are six faces, like six different possibilities, so 6 into 6 is total possible, 36 outcomes are possible.
Yes.
So probability of 1 comma 1 is 1. So similarly for this is another outcome, so 1 by 66. So you add them up together, so that's how you calculate, right?
Hmm.
So for this case, this is the probability of either the path can be from S2 to S2 to S1, or so whenever there is or there is addition, like that, plus S2 to S1 to S1. Do you see this?
Yes. This I understood.
Okay, now also these transitions which happen, they are like independent events. Okay, so
Okay.
like S2 can independently, it can either go to like S1, or it can go to, it can stay at S2. So it's like independent, like it's like that. So we use the property of independence of probabilities while studying DTMC, discrete time Markov chains. So now how do we find these probabilities? Probability of S2 to S2 to S1.
So S2 to S2 is 1 by 5.
Yes, 1 by 5. And basically my point is
Hmm.
this chain of probabilities can be decomposed into product of two probabilities, okay, because it's happening in two steps. Okay, so this is probability at first step, S2 is going to S2, I mean it's staying at S2, times probability
Hmm.
S2 goes to S1,
Okay.
correct?
Yes.
So this is like in the first step I have added, because this is like two options, either this or this. But for this event to happen, this entire chain series to happen, they both must happen. So that's
Yeah.
why the
So there is
product.
and. There
This
is
is
and.
exactly. So that's
Yes.
the difference between like and or.
Or,
Okay.
huh.
So yeah, so this is the chain you see from S2 to S2. I mean S2 staying at S2 after the first transition, and then S2 making a transition to S1, their product. Similarly, you tell me about the second term.
So probability of S2 to S1
Correct?
multiplied by probability of S1 to S1.
Yes.
Divided by 5.
Now you check these values and you can easily.
Okay.
So this is probability of S2 to S2 means P22.
Huh.
Probability to S2 to S1 means P21. S2 to S1 is again P21. S2 S1 to S1 is P11.
2 4, 8, 5, so that will be 75, 12, and 40. So 52 by 75, that is what I'm getting.
Uh, how much?
52 by 75.
Exactly. Yes. 52 by 7. So this is 52 by 75. So this is your answer, and easily, I mean, the correct option you can verify it's option B.
Yeah.
But so this is how, like, I mean, you can follow the sequence of steps how it's happening and okay, write it like this. But you can also do it alternatively. Alternately, what you can do, you can first form the two-step transition probability matrix. Like this starting matrix that you had, matrix P,
Hmm.
this is the one-step transition probability matrix. So which means like S1 to S1, S1 to S2, S2 to S1, S2 to S1. Only one transition is happening.
Hmm.
Okay, those probabilities.
Hmm.
Now, after two possible transitions, what are the corresponding probabilities that you can capture using another 2 cross 2 matrix, which is the two-step transition probability matrix. Okay, so it's like the first entry of this would be like probability of S1 going to, I mean, either via S1 S1 or like probability of S1 to S2 to S1. Like starting point is 1, ending point is 1. Starting point is 1, ending point is 1. So this will be the 1 comma 1th entry of this new matrix, two-step transition probability matrix. You see?
Okay. So P12 will be S1 to S1 to S2 plus probability of.
Okay, so you need not compute these individual values. So
Okay.
I mean the way to do it, like you can find the two-step transition probability matrix as simply you square it. Okay, you raise p to the power 2. If it's an m step, you raise p to the power m. 3 step, p cube. 4 step, p to the
Oh,
power 4. Okay, so this is p times p. This you know, p you know, right? So this is
yeah. So P.
this times this, and this will be in terms of fraction 32 by 45, 13 by 45, 52 by, sorry, 52 by 75, 23 by 75. And here also, if you look at every row, the sum of the entries of the row, they also equate to 1. You see in this p square matrix, two-step transition probability matrix,
Yes.
right? That property always holds.
Yes.
Whether it's p square, whatever, that always holds. So now look at this matrix. Look at this entry.
Huh.
This is exactly the answer that we got, right?
Yeah, this is what we got. Yes.
And why? So this is the 2 comma 1th entry, right? This is the 2 comma 1th entry of your p square, two-step transition matrix. This is equal to 52 by 75. And 2 comma 1 makes sense because what you are asked is like you are starting with state 2 and ending in state 1 and going to state 1 in 2 steps. You see, that's what we did here. I mean,
Yes.
there are two possibilities, S2 to S2 to S1 or S2 to S1 to S1. So numerically we found out, okay, 52 by 75, or just we first, I mean, found the matrix of two-step transition probabilities and then looked at its corresponding entry, 2 comma 1th entry, which gives you the same thing. Let's say if you were asked starting from S1 and going to, I mean, staying at S1 itself in 2 steps, then it would have been this first entry, 1 comma 1th entry of this p square, which is 32 by 45. Okay.
One going to S1 and
And staying, I mean, ending at S1 itself. I mean, starting with S1 and ending at S1 in 2 steps. If this would have been asked,
huh.
then
Okay. We will
then
add. Hmm.
then it would have been like 32 by 45. So because that's the 1
Oh.
comma 1th entry of this p square matrix, right?
Hmm. Yes. Understood.
Because, and if you want to, calculate it separately, so it can happen like either this or
Hmm.
S1 to S2 to S1, like this, correct?
Yes. Like we calculated.
Exactly. So this is like, let's check anyways. So again, this probability you can decompose it S1 to S2, S1 to S1. So which means probability
2/3.
S1 to S1 times again probability S1 to S1
Third into 2/3 plus uh, 1/2 into
and S1 to S1 happens, it's like P11 times P11 plus P12 times P21. So this, if you do it, 2/3 times 2/3, that is 4 by 9, plus P12 was 1/3 and P21 was 4/5. So this is 4 by 15. LCM is 45, 620 plus 2, 12, 32 by 45, which is exactly the 1 comma 1th entry of this p square matrix. Okay, I think it's not clear.
64. No, I messed up the calculation. Yeah, it's clear. 32 by 45.
Okay, why I wrote it like this, do you see? Like, I'm just considering a separate case, starting from,
Yeah,
this
yeah.
is different situation, starting from S1 and ending in S1 in
Yes.
2 steps.
Yes.
This is this event, and this
Yeah.
is a probability 32 by 45 for this event. Okay,
Yes.
so
Yes.
I think the second method is relatively quicker. I mean, you just have to, for a 2 by 2 matrix, it's like computing the product is, I think, quicker, I think.
Yes.
So you can find that, and correspondingly the I comma jth entry of p square will tell you the probability of starting from state I or Si and ending in state Sj in 2 steps.
Okay.
Okay, so the I comma jth entry of p square. So this term, what does this mean? I comma jth entry of p square. Okay, this is the probability, or I should say transition probability, or two step transition probability, because p square, right? Two-step
Hmm.
transition probability of starting from state Si, that's the first index, and ending in state Sj. Okay,
Starting, 1 minute, I'll write this two-step probability of starting from state is I and ending in state is Z. Yes.
this is what we are doing. I mean, p square, I mean, because we are asked about two-step transition, that's why we are looking at the entry of p square. If it's in general some m step transition, then you have to look at the I comma jth entry of p to the power m. Okay,
Hmm. Yes.
so this is just a case of 2, that's why I wrote 2. But
Hmm.
yeah, so the answer, as we saw, is option B.
Hmm.
Answer is, maybe I'll write here, option B. So is this clear?
Yes, yes, yes. I understood everything.
Okay, good. So let's now move on to the second one. So you see, these are easy things only.
Yes.
Okay, now I'll even prove this why it's easy. Okay, with the second question. Okay, so what we are asked in the second question is, which of the following matrices can represent the transition probability matrix for a discrete time Markov chain, DTMC? Which of these following can represent a transition probability matrix, which means which of these following is a possible or is a valid transition probability matrix for a DTMC? So can you guess which one of these? Just think about the properties and all.
So,
Can you straight away eliminate one
either,
of the options?
yeah, A and C I think can be eliminated because they do not sum up to 1.
Okay, great.
So
Their
B,
rows do not, the entries of the rows do not sum up to 1. Correct.
yeah, and B and D can be correct answers.
Can B be correct? I mean, do
B.
you see like a thing in B which is not
Oh,
present in D?
uh,
There is one factor in option B which is not present in any of the three options, A, C, D.
negative. Oh, probability cannot be negative.
Exactly.
So
And
it is
also, and also, and also, there are two entries which are more than one, greater than one, 1.2 and 1.55.
1.2. Correct, correct. I was just looking at the sum should be 1, but that,
Yeah, yeah, yeah. So even if you are not aware of the property that the sum should be one, you can also, then also you can eliminate option B just by, seeing that this is not a valid probability. Okay.
yes, correct. Understood.
Okay. So option A and C you already eliminated using the row sum property, and option B is also eliminated. And for option D, you see it's totally valid.
Yeah,
The rows are summing up to 1, and these are all probability
yes,
values,
yes,
valid probabilities.
yes.
So just by looking, you are able to find the answer. So this I'm just writing the right answer.
Yes.
This was the right answer, 0.95 and 0.05. So this matrix, if this is in general, if it's not mentioned, you assume that this is the one step transition probability matrix. And if you look at this matrix, this tells you that there are two states. There are two states, right? It's
Two
a
by
two by two, so there are two possible states. And if I assume that this is the one step transition probability matrix, that means like from P11, that is probability of S1 going to S1 itself, is 0.95.
two.
P12, probability of state S1 going to S2 is 0.05. P21, which is probability of state 2 going to state 1, is 0.90, and
Hmm.
probability S2 staying at S2 is 0.10. Okay, that's the
Yes.
like. So here, like, all entries are
Between 0 to 1.
exactly probabilities lying between 0 and 1, and secondly,
Row wise addition is 1.
sum of entries
Yeah.
in every row is equal to 1.
Yes.
So this can also be, I think, if you want to mathematically write it, P I J summation j running from 1 to, in this case it's 2, so uh, yeah, so 2 1, okay, yeah, that is equal to 1 for all I. In general it could be like j
Oh,
running from 1 to capital N for
okay.
all I. For, so what does this tell you? Like for every row, the sum of the elements of the row should be equal to 1. This is exactly the same thing I have written in this
Hmm.
compact form. So
Hmm.
let's say for all I, right, I wrote, I mean possible I values is like I1 and I2 because there are two rows and two columns here, right?
Yes.
So let's say if I is 1, what does this sum give you? This sum will give you j running from 1 to 2 P1j, because I'm choosing, let's say, I equals to 1
Hmm.
for the first row. So this is nothing but P11 plus P12. So that's the element sum of elements of first row, which is 0.95 plus
Hmm.
0.05.
Hmm.
This is 1. And for the second row, for I equals to 2, this sum is summation
It-
P2j,
hmm.
which is P21 plus P22. P21 is 0.90 and P22 is this. So this is again 1. Okay.
Yes.
Okay. Okay. So then moving on to the next one. Um, okay. Yeah. So this is again a DTMC problem. Mm, again, it's a simple problem of two states. Okay. So the problem is like weather modeling. Okay. This DTMC is trying to is used to model a weather. So where the state on the nth day, so the time instant here is like a day, okay, like the nth day, day n, the state is given by w suffix n. Day n plus 1 on the next day, it's like w n plus 1, it's like that. Okay, so previously we were using the variable capital X for the state. I mean it's like a random variable only, right? So but here the capital W is used. That's the only difference with respect to the notation. So W suffix n denotes the state of the weather on day n. Okay,
Hmm.
and there are only two possible states here. See the state space, it is either S1 or S2. Okay, so this Wn, the state can be either of these two, where
Hmm.
S1 denotes sunny weather and S2 denotes rainy weather. Two only possibilities.
Hmm.
Now if you are given that if given a particular day is sunny, let's say the current day, the present day, if it's sunny, then the next day can be rainy with a probability 0.25.
So do we say that P12 is 0.25?
Yeah, exactly. From sunny to rainy, transition happens with a probability of 0.25, and
Hmm.
by our notation we are denoting S1 as sunny and S2 as rainy, so therefore exactly P12 is equal to 0.25.
Hmm.
Okay, so that
Yes.
automatically tells you what is P11. It's simply 1 minus that, right? I mean
Oh, yeah.
0.75. So it can either go from S1 to S2 or it can stay at S1.
Yes.
So this whole thing can be characterized using a 2 by 2 transition probability matrix, right? One step transition probability matrix, because there are only two states. And this is exactly what you said, P12. So that's the 1 comma 2th entry of that matrix.
Yes.
And immediately by looking at its value, by knowing its value 0.25, I can tell what is P11. So that's the
Yeah.
other entry of the first row. So that should be 1 minus that, which is 0.75, right?
Yes.
Okay. Now the next part says, while when a particular day is rainy, the next day can also be rainy with a probability of 0.15. So what does this mean?
P22.
Exactly. So this is P2 to 0.15.
So P12 is 0.85.
Not 1 2, 2 1.
Sorry. Yes.
Yeah. Okay.
P2. Yes.
So
Okay.
P21 is 1 minus 0.15, which is 0.85. Now you have all the entire matrix actually.
Yes.
And that's exactly what you have been asked. The one step transition probability matrix for DTMC is what? Okay. And even here also you can straight away by looking at the options, you can eliminate option D,
Yes.
because that sum
The
of row
first row,
property is
yeah.
not.
First row is less than 1, second row is greater than 1 of option D.
Yeah, I mean, yeah, the sum is not equal to 1. That's the thing. So
A option is correct.
A option is correct, exactly what we saw here. Based on what we just found, option A is the right answer. So just you have to be a bit careful, because in case you would have like that S21 and S2, S12,
Ah,
if you confuse, then you'll get a different matrix.
yes.
But it's like you can cross check also. If you arrive at a transition matrix, then you can cross check also that whether okay the sum of every row is equal to 1 or not. So that's a, I mean, double verification. Okay, so now let me write it. So again, this is a DTMC problem where a Wn denotes the state of the weather state at time instant n or on day n. Okay,
Hmm.
here the time is basically the that particular day. Okay, so this, and the state space is S1, S2. So n equals to two states. Okay, and yeah, so S1 denotes sunny weather, S2 denotes
Rainy.
rainy weather. Now what you are given is, given a particular day is sunny, the probability that the next day will be rainy, which is exactly P12, is equal to 0.25. So probability do you see this? This is the same as P12.
Yes.
So this is at present day, this is sunny weather state, and the next day, which is n plus 1, the state is rainy. This is exactly P12. So this is given as 0.25, and immediately from that sum of rows should be 1, that property, or simply, I mean, by logic of probabilities, because there are only two possibilities, so this tells you that P11 should be equal to 1 minus P12, which is 0.75. Okay, and also, given a day is sunny, sorry, given a day is rainy, the probability that the next day is also rainy, it can be written mathematically like this,
S2. Wn is equal to also S2.
because S2 is rainy as per our notation, as per the question. Okay, so this is your P22, which is given as 0.15. So
Hmm.
P21, which means from rainy to sunny,
Hmm.
that is basically 1 minus P22, which is 0.85. Now you have the complete matrix. So therefore, one step, so one step transition matrix, right? We are making only one transition. Okay,
Yes.
so you expect it to be a 2 cross 2 matrix, right? Because there are two steps, is P equal to P11, P12, P21, P22.
Hmm.
Okay,
Yes.
option A. Okay, now moving on to the fourth one. Okay, see again a similar problem. So we are dealing with two states only so far, which is like the simplest case, right? So what do you think here? And again, can you eliminate some of the options? Because we are asked to find transition probability matrix for DTMC.
Yes.
Straight away by looking at some options, can you eliminate?
C will be eliminated
Okay,
and A also will be eliminated.
correct.
And
So at this stage you can't. You have to now read the question and then arrive at your answer among B and D. So see what is given in the question.
P11 is 0.2
Correct.
and P21 is also 0.2.
Correct.
So P12 should be 0.8 and P22 should be 0.8.
Correct.
So B is the answer.
Yes. Right. Correct. Absolutely right. So, two-state DTMC. This was a two-state DTMC problem. Okay, two-state DTMC problem. Two-state. So capital N is the typically we use capital N to denote the number of states. That is equal to 2 here. So your transition probability matrix would be 2 by 2 matrix when it's an n by n matrix. So 2 by 2 here. You are given probability of these both are equal to 0.2. So I'll go to the next page. So this is nothing but P11 and P12, they are both equal to 0.2, and you can immediately deduce the other probabilities. Sorry, this should be P21, right? P21 from 2 to 1 transition, that conditional probability is given. Okay. Yeah, so this is 0.8. So your P should be okay. Shall we move to the next one?
Yes, sir.
Okay. So this is question number 5. Okay. Okay, so here also we are given the one-step transition probability matrix for a DTMC, and it's a 2 by 2 matrix, and if it is a valid transition probability matrix, as you can see the properties are satisfied: 2/3, 1/3, 1/6, and 5 by 6.
Yes.
And we are asked to find two-step transition probability matrix. What to do we know, right?
Yes, so P square we do.
Exactly. P squared is what we need to find.
And 18.
So the one step transition probability matrix of a discrete time Markov chain is given as P equals to 2/3, 1/3, 1 by 6, and 5 by 6. Then you are asked to find the two-step transition probability matrix. that is simply your p square, which is p times p. I mean, that's why it's like a chain, you know, we use the term chain here. Like it's like a chain of like transitions which is happening. So here you can take the products like this. So this is simply multiplying this matrix with itself. So this is the right answer, and it actually matches with the option C. Okay. So the fifth question was fine, right?
Yes, yes.
Okay.
So here first we need to write the probabilities.
Correct. Yeah. I mean, in this case, you see, like we have a different representation
Hmm.
of the Markov chain in terms of the state transition diagram. So
Yes.
this is one way of representation of modeling, and another way is using the state transition, like the transition probability matrix.
Yes.
So all these values actually you see here are actually the entries of that uh, matrix.
Yeah. Like P11 is 1/4.
Correct. And in this case, it is a 3 by 3 matrix because there are three possible states. You need
Yes.
three
Correct.
possible states, 1, 2, and 3. Like
Hmm.
instead of S1, S2, S3, we are denoting, let's say, 1, 2, 3 as the states.
Yes.
And this has this following state transition diagram. And you can construct the state, like the transition probability matrix as well by looking at this diagram.
Yes.
And you're asked to first find what is probability that x4 equals to 3 given x3 equals to 1. So which means at time instant 3, like what is the probability that you go, given that you are in state 2 at time instant 3, you go to state 3 at the next time instant, which is time instant 4. So that's what you're asked. What is the transition probability from state 2 to state 3? So just by looking at this state transition diagram, can you tell me what is the answer of A?
Is it 2/3?
From 2 to 3, you have to see. So yeah, it is 2 by 3.
Yeah.
And as we saw, like it doesn't matter, the index here, xn, that index n doesn't really matter because of the time homogeneity property, which I mentioned before on the
Yeah.
very first slide. So
Yeah. Like we are considering from like 3 to 4. In this case, they have asked
correct,
3 to 4. It
correct.
can be 1 to 2. It can be 2 to 3. Anything.
Yeah. So what's important here is that like is the immediate next step, and it's like the immediate next time instant. That's why these are like one step transition probabilities.
Yes.
If you are asked, let's say probability x5 equals to 3 given x3 equals to 2, then it's a two-step process
Yes. Yes.
because x5 denotes like the state at time instant 5, whereas x3 denotes state at time instant 3. So there has been like two steps transition has occurred while
Yes.
going from x3 to x5.
Yes.
Okay, so now so we are in question number 6, and the given state diagram is like this. So there are three states. Three states are state 1, state 2, state 3. Circle like this. These are like nodes. Okay, so there is a self loop.
Yes.
So state 1 goes to state 1 to itself with probability 1/4. State 1 goes to state 2 with probability half. State 1 can also go to state 3 with probability 1/4. Now state 2 can go to state 1 with probability 1/3. State 2 can go to state 3 with probability 2/3. Yeah, and these are the only two possible cases, and state 2 doesn't like go back to itself, so that probability is 0 here. So you see the sum of the probabilities associated with the branches that are emerging from node 2 is like 1/3 and 2/3, so they add up to 1. So which means like the self loop is not present here.
Yes.
This happens with probability 0. Okay,
Ah.
because I already have the other two cases which add up to 1.
Yes.
While if you look at node 1, there are like three possibilities. It either goes back to itself, or it goes to state 2, or it goes to state 3.
Okay. So one half plus quarter by quarter, so it makes one. Yes.
Exactly.
Yeah.
And that they must add up to 1.
One. Correct.
Then only your sum of every row of that transition probability matrix would be 1. I mean, that exhausts all the possibilities, right? So they must add up to 1.
For three, we should find out what is 3 to 3 because one fourth and 2/3.
Yeah, I'm still yet to finish the diagram. So
Yeah.
from 3, it can go to itself. There is a self loop with probability 1/2. So, and it can go to node 1 or state 1 with probability 1/2. That's it. Half and half. So it can't go to state 2. So this is the
And
state transition diagram.
two.
State transition diagram. So we typically encounter these kind of diagrams in many fields, be it in electronics, where you are studying Boolean algebra, digital electronics, state 0 or 1, how, I mean, it can change its state. Okay, let's say there are two possible states, 0 and 1. So instead of, yeah, so that might be the simplest case. Or, yeah, it can be two states as well, 0 0 0 1 1 0 and 1 1 if you are in binary. So there will be like 4 nodes, and each node it can go to other node with some probability. In communications, if you look at channels, there is a very popular channel called binary symmetric channel, or BSC, where like you are sending either bit 0 or bit 1, because it's binary symmetric channel, right? So there is like two possible bits. Binary means like binary digit, 0 and 1. So you are either sending 0 or 1. So let me draw it here also. Okay, so the binary symmetric channel, BSC. with probability p. P is the transition probability in that case. So what you have is at the receiver side, you have, let's say, bit 0 and bit 1. So bit 0 stays as bit 0 as it reaches the receiver. So this is transmitter, this is receiver. In between, what is the channel sits, okay? So zeros can also make a transition to 1. So that's what we call as error, like bit flip error. So 0 goes to 1 with transition probability p, and 0, then 0 stays at 0 with probability 1 minus p.
Hmm.
Similarly, 1 stays as 1 with probability 1 minus p, and 1 makes a transition to 0 with probability p. Okay, so this is how a binary symmetric channel is characterized.
Okay.
The parameter is p, which is the transition probability. So you see, this is also kind of a, simple diagram where we have like nodes and states doing some transitions with associated probabilities and all. So yeah, and also as I said about analog, like, sorry, about digital electronics, you encounter such state transition diagrams. And even in like control systems also, if you have gone through, like, there are some state transition diagrams there, uh, where we can actually, yeah, we use kind of nodes and branches there. It's the same concept there also. So
Yes.
yeah, so state transition diagrams, the point is like they occur in like a plethora of cases. Anyways, so I mean, this is just aside, nothing to do with the problem.
Okay.
And anyways, let me just mention binary symmetric channel.
Sir, one thing I'm getting confused.
Uh-huh.
In this blue
Hmm.
image, we only consider which arrows are going out from the state. Like for two, we only consider one third and two third. That upper half is
Hmm.
not related to state.
No. Yeah, so this direction of the arrow is denoting the transition. Okay, so the arrowhead you have to see. If the arrow is pointing, if the arrow is, let's say, emerging from node 1 and it
Hmm.
is directed towards node 2, let's say this arrow, okay,
Ha,
I'm
ha,
considering
ha.
this arrow. So this
Yeah.
is emerging from node 1 and it is directed to node 2, so that means it is a transition from 1 to 2,
Okay.
right? So this arrow is telling you.
Okay. So it is counted for node 1 and not for node 2.
No, it's
Okay.
basically probability 1 to 2, p1 2.
Yes. Yes.
That is
Yes.
how.
Yeah.
Okay,
Yes. 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 Got it. Yeah. Yes, sir.
the branch, the arrows, the edge actually emerges from the starting node and ends at the final state.
Okay.
that
Yes.
that is what is happening.
Yes.
Okay, it's basically a directed graph.
Hmm.
Okay, so let me just remove this red line. Okay, so this is the state transition diagram for our DTMC. And how many states are there?
Three states are.
Three states are there. So one, two, three, three possible states.
Yes.
So this automatically tells you that your state transition probability, say one step transition probability, capital P, should be a, what should be its
3
size?
by 3
3
by
by
3
3.
matrix.
So n is 3 here. Okay. Now, and in fact you can construct p also straight away. So what would be the entries? P11, P12, P13. That's your
Hmm.
first row.
Yes.
Second row would be P21.
P1, P22, P23.
Okay.
Yes.
And just by looking at the state transition diagram, you can put these values. So 1 to 1, P11 is this self loop, which is 1/4. P12. So P12 means from
Half
1 to 2,
one.
that is half. So that direction of the arrow is important. Now P13 means from 1 to 3. So from 1 to 3, what is the arrowhead? It's like this, you know,
One
this
fourth.
1/4, yeah. And it makes sense because if you add up these elements of the first row,
Yes.
you get 1.
Yes.
Now what about P21? P21 is how
One,
much?
one third.
1/3. P22 is how much?
P22, there is no arrow.
It's 0.
Yeah, so yeah, it's zero. There is no, yeah.
That's what I mentioned during this while drawing this state diagram. No, I mean there are only two transitions that can happen starting at uh, the second state, state 2. It can
Hmm.
either go to state 1 with probability 1/3, or it can go to state 3 with probability 2/3. So they add up to 1. So these exhaust all the possible cases. So this self loop is not present here.
Yes, so that is zero.
So once you arrive at 2, at the immediate next step, you have to make a transition either at state 1 or state 3.
Or three. You cannot remain in state.
Exactly. So this is kind of an unstable state. Okay.
Okay.
So yeah, you can think of it like that. Once you arrive at that state 2, and also there is only one way of arriving at state 2. If you see, if you look at the arrowheads, you can arrive at state 2
Only
only via state 1.
state one. Hmm.
So once you arrive at state 2, at the next transition, next step, you have to make a transition. You can't stay at state
Hmm.
2 any
Hmm.
longer.
Hmm.
Okay, so P22 is 0. And what about P23?
It is two third.
2/3. P31, 3 to 1.
3 to 1 is half.
P32,
It is zero.
0 because there is no such branch.
Yeah. And 3 is again half.
Yeah, that's self loop.
Yes.
Okay, and this is a valid transition probability matrix.
Yes.
So this is my one step transition probability matrix.
Hmm.
Okay, now coming to the question. So this is just a thing which I did, like I constructed this matrix, although I was not required to do so yet. So in part A, you are asked what is the probability of this transition.
Hmm.
So this is simply probability state
Two.
2 going to state
Hmm.
3 in the next step. That's it,
Hmm.
in one step. And
Yes.
from the diagram, this is clearly like P23, and we have also constructed the matrix,
Hmm.
right? So P23 means
Two.
starting from 2 and going to 3. So that's basically this entry, 2/3.
Yes. Two third. Yes.
And from the diagram also you can see
Yeah.
starting from 2 and going to 3 is this path, which is 2/3.
Hmm.
And now the second part, what is probability of x3 equals to 1 given x2 equals to 1?
So 1/4.
1/4. Exactly. I mean, at the time instant n, I mean time instant 2, it is at state 1, and at the next time instant, which is time instant 3, it stays at state 1 itself. So that's basically the probability of the self loop, which is p11, which is 1/4. So probability x3 equals to 1 given x2 equals to 1, and this is also the same as, you can also rewrite it as probability of x4 equals to 1 given x3 equals to 1.
Yes.
Doesn't matter,
Yes.
as long as there is a difference of one step, it's fine.
Hmm.
This and that property is actually called the time homogeneity property.
Yes.
So this is 1 to 1. So 1, I'm just maybe using different notations just not to confuse, because this is 1 to 1. So P11, and that is that self loop probability 1/4.
And yes.
Now coming to part C. Okay.
And P x0 1 to x1 is equal to 2.
Okay, what does this mean?
So if we know that probability of
X
uh,
naught, x naught is equal to 1, that probability is 1/3. Let's say we know. So the initial state, I mean at time instant
uh,
0, so that is x naught. The state at time instant 0, it is x naught,
uh,
right? Because at time instant n, the state is given by xn. So at time instant 0, you can think of it as the initial state, which is
hmm,
x naught. Let's say that state is equal to 1. That happens with probability 1/3. Let's say you know this.
hmm.
If this is the case, then what is the probability that x naught is equal to 1 and x1 is equal to 2? I mean, this is like a joint probability, like, I mean, both should happen.
So yeah, so we consider 1/3 and we multiply by 1/2.
Exactly,
Okay.
exactly, exactly. So
Oh,
it's like starting at state
uh,
1 with this
hmm,
given probability, which you already know 1/3,
hmm.
and making a transition from 1 to 2, which is
Yeah.
clearly from this diagram, it's given by
Yeah.
1/2.
One.
So it's basically product of 1/3 and 1/2, which is 1/6.
Yes.
So what we are given is probability x naught equals to 1. This, if it happens with probability 1/3, then what about this? So what this is telling is like the event is basically starting with state 1, and I mean at time instant 0 it was 1, and at the next time instant, which is time instant 1, it is 2, right?
Hmm.
So
Yes.
starting with state 1 and going to state 2, okay,
Hmm.
in the immediately next step.
Yes.
Okay, so that is nothing but probability of x naught equals to 1 times
Yes.
probability you are making the transition now. So that
Hmm.
is probability x1 equal to 2 given x naught equal to 1,
Yes.
right?
Yes.
And this is also, if you go back to your high school mathematics, this is
Hmm.
typical, the in while learning Bayes theorem and all, Bayes rule and all. This is like a probability of A intersection B, like joint probability. It's simply like probability of A times probability of B given A. It's like
Hmm.
that.
Yes.
It's the
Yes.
same thing here.
Oh, yes.
It's a very similar thing which is happening here.
Hmm.
Okay, fine. I mean, let's not get confused anyways. I mean, the point here is that, okay, you're starting at time instant 0 at state 1, and then you are making a transition to state 2 in the immediate next time instant.
Yes, sir.
So this is given by the probability of these two, which is, okay, now the first part is like 1/3, which is given, times the transition probability is nothing but p12. So this is, and p12 from the diagram you can tell that it's 1/2, 1/3 into 1/2, which is 1/6. Okay. Okay. Now a similar question is the part D, which tells you again, okay, you are starting initially at state 1 with probability 1/3. Okay, at time instant 0, you are starting at state 1 with probability 1/3. Now find this probability of the sequence of transitions. Okay, now how many transitions are there?
There are two transitions now.
Exactly. So now there are two transitions, from 1 to 2 and then from 2 to 3. At time instant 0, you are in state 1. At
Hmm.
time instant 1, you go to state 2. And on the immediate next time instant, which is time instant 2, you go to state 3. So basically it's 1 to 2 to 3.
Yes.
So it's 1 to 2 to 3. So it's like um, 1 to 2 to 3. So it's like this path. So from 1 to 2, this is only one possible way,
Yes.
and from 2 to 3,
Also one possible.
this. So this is what is happening.
So one by two into two by three.
Okay, okay, okay,
Hmm.
okay. Just a second, just a second, just a second. Ah, right, right, correct. So this is the path. Okay, the in green.
Yes.
Let me remove it. Let's not, I mean, confuse with the original diagram. So that's how the path goes.
Oh, yes.
So that clearly from that, if you, okay, let me, if I draw that again. So what are the corresponding like branches you encounter?
One by two into two by three. And
Yeah,
initial also we have to.
yes. So initial like 1/3, that's the starting probability that you are given.
Hmm.
So that also you have to multiply. So one third, which is the initial, times the first branch from 1 to 2, which is half, and then
Hmm.
from 2 to 3, which is 2/3. If you take their products, it will be 1 by 9 actually. One third times one half times 2/3. So that's basically one third, 1 by 9.
Yeah.
So yeah. So that just by looking at the diagram you can do that, or else if you want to mathematically, yeah, anyways you'll need the probability values. So this is given at, you're starting with state 1 with probability one third at time instant 0. What is this probability? So this means starting from state 1 and then going to state 3 via state 2.
Yes.
So it's like this 1 to 2 to 3, this transition.
Hmm.
Okay.
Hmm.
So, sorry. So this is the thing. So how can you break down this probability? So the first starting point is probability x naught is equal to 1. And similarly, as we did for the previous one, we broke down into two products, right? Like this.
Yes.
And then
So, two.
now you have to multiply with the transition probability, with the conditional probability.
So,
You are ultimately trying to reach
huh.
x2 equals to 3 given your prior states. Your prior state,
One equal
x2 equals
to.
to 1, x2 equals to x1 equals to 2, and x naught equals to 1.
Yes.
Okay,
Yes.
this is what is happening. So you're arriving at state 3, that's your final state, through a sequence 1 to 2 to 3. It's like that.
Okay.
Is this step clear?
Yes. Yes. Yes.
Okay. Now again what we can write, I mean, in exam you need not do it all this, unless you are asked to solve it in detail. You
Hmm.
can, for writing the answers, it's just you just look at the diagrams and then figure
Hmm.
it out easily. So that
Hmm.
way you can save time just using some tricks and all.
Yes.
But I'm just, for completeness, I'm showing these things. So this, now this transition probability, this condition probability, you can also rewrite this second part actually.
I was just wanted to ask that can we split this x2 is equal to 3
Hmm.
given x1 is equal to 2 in one bracket into p of x1 is equal to 2 given that x naught is equal to 1 in another bracket.
Okay,
Can we
so we are saying this second term can be whether rewritten as, go again,
x1 is,
x1.
yeah, because it is x1 is equal to 2.
Yeah, tell me the expression.
Second will be what I'm thinking is p of x1 is equal to 2 given that x naught is equal to 1. Yeah, 1.
Okay.
And the in between this red and blue, it should the first one that probability of x2 is equal to 3 given that x1 is equal to 2. Can we write it like this? because there are two steps.
Yeah, I mean, at the end of the day, there will be like product of three probabilities. I mean, you're starting with the initial probability that is given,
Hmm.
then the probability which is like 1 to 2 transition, and then another probability which is the 2 to 3 transition.
Okay.
Their
Yes.
products you have to take. I think you also mean the same thing. I mean, you are also trying to say the same thing,
Yeah. Yeah. Yes. Yes.
right? So, yeah, that's true. That's true.
Okay.
That's exactly what I'm going to do as well. But you see, like here another like observation here is that
Hmm.
in this second term you can actually use the Markov property. What does that Markov property? If you go back to the slide 1 where I mentioned the Markov property,
It
only the
depends on
most
the task.
recent
Yeah.
that matters.
Yes.
Okay, so you can discard the older
Previous
ones,
ones. Yeah.
older states. So only the immediate state will
So
matter.
only we consider 2 to 3.
Exactly. Sorry. So this is okay.
Hmm. Then we'll our answer should be same, no? Our answer should be 1/3. I think first one was 1/3. It's not equal to 1. And
Okay. Sorry, sorry.
oh yes, yes, that was.
No, no.
I got.
I missed a step actually here.
I think I got that it was 1/3 into 1/2 into 2/3. So that two is getting cancelled.
Ah,
And
right, right, right.
right?
No, I mean in this step I actually missed a term. So I'm just right. We already have the answer 1/9. We just saw it diagrammatically, but
Hmm.
just mathematically. So in this step actually I missed out a term. So this actually it's it's like a two-step transition, right? So you're starting with x naught at 1, that probability which is given to you 1/3. Then you are making, so now you are at state 1, right? At this stage, the starting point. Now you have to make a transition from 1 to 2, okay?
Yes.
Because this is the path which we are looking at 1, 2, 3.
Yes.
So now you have to make at the next time instant from 1 to 2 this
Yes.
transition,
Yes.
and on the next time instant, that is the time instant 2,
Yeah.
you have to
5.
make a transition from 2 to 3, state 2 to state 3.
Yes.
So that is x2, that's the final state at time instant 2 is in the state 3, given your past like records, like past states, which is like
Uh-huh.
x1 being 2 and x naught being 1. Okay,
Oh. Okay.
I mean that's how you
For
like,
last.
this is the chain rule of like conditional probabilities, right? I mean
Mhm.
that's how you keep track. But again, now we can use the Markov property, this term
Okay.
actually, where only the, I mean x naught is not relevant here in this second term. So this is the same as actually probability of x2 equals to 3 given x1 equals to 2
Hmm.
by Markov property.
Yes.
So in the last time I actually missed out this middle term.
So when there are two transitions, we have to write for the final, that is third state.
Hmm.
Even that first to both the conditions we have to mention, at least when we are writing first time, and then we can say that by applying Markov, then
Yeah,
we are
yeah,
going
yeah,
to
yeah. I mean, yeah, I mean, just for completeness, I'm showing, but
yes.
here it's like ultimately the expression which I am writing in this step right now,
Hmm. Hmm.
it's just like this. I mean, mathematically, this is how like you should. I mean, in this step, how I have expanded it completely. This
Ah,
is how you should expand a conditional probability because
yes.
in our case, it happens so that okay, the older states are not affecting the immediate next
Hmm.
transition.
Hmm. Hmm.
Okay, but it might influence. But
Yes.
in our case, this is a simple case because of Markov property. Only the immediate past sample is relevant in our case.
Yes. Yes.
So x naught will not affect x2. That is my point. So I
Yes.
can discard that.
Hmm.
So this is simply probability of x2 equals to 3 given x1 equals to 2,
Yes.
right? So yeah. So now we know these probabilities. This is given as one third probability of x naught equals to 1. You're
Hmm.
starting with one third probability and at state 1, and next time instant you make a transition from 1 to 2, from 1 to 2, so the probability is 1 half,
Hmm.
and on the next time instant you make a transition from
3.
2 to 3. From 2 to 3 is nothing but p23, that in terms of the matrix also you can see, or from the state
Yeah.
diagram you can see that's 2/3.
Yes.
From the matrix also you can see that's 2/3.
Yes.
So whichever way you feel, so this is 2/3. So 2 gets cancelled and we get 1 by 9.
9.
Same
Yes.
answer again.
Yes.
Okay. So yeah. Okay, I think with this we have yeah, we have completed all the problems for today.
Yes.
Uh, yeah, are there any queries or anything?
No, no, sir. I understood everything. Thank
Okay.
you so much. Yeah.
Okay, great, great. Then I think we can maybe
Yes.
stop, and I think there will be two more sessions.
Okay.
Next week there will be like the 12th live session.
Hmm.
So last week's contents mostly, and there will be one more session probably on next to next Friday, which will be like an extra session.
Okay.
So we'll see. Maybe that day we can just have maybe instead of solving, or we'll see. Maybe we can solve a few questions based on the past topics that we have also looked at for
Yes.
revision or something. I have not yet decided what to do, but
Okay.
at least for the next week, upcoming week, we will go for week 12 contents as per the
Yes.
usual flow.
Yes. Yes. Yeah. Yes,
Okay.
sir.
So then let's meet again on coming Friday, 6 p.m.
Yes. Thank you, sir. Thank you so much.
Okay. You're welcome. Thank you.
Bye. Bye.